And this morning I recorded one of my lectures and it didn't record any of my writing, like any of my Apple Pen. So let's hope that it does this time. So let's see here, share screen and start broadcast. Let's see how it goes. And if there's at any point, if you have a question of something that you want to look at specifically in greater detail, or just any question in general, I'm happy to stop and take a look at that. Well, let's start with question number 53, which asks, simple question. Oops, where are we? Oops, I'm already botching it. There we go. Question number 53. And question number 53 says, what requirements must a carbon atom have to be chiral? And this is one that just requires some hardcore, straight up memorization. And the carbon atom, it must, so let's write it down, it must be attached to 4 unique, not unique atoms, but unique groups. So 4 unique groups. So if we come up with an example of a chiral carbon, so let's say we have a carbon and it's tetrahedral, and let's say we have a chlorine, let's say we have a methyl, and let's say we have a proton, and then let's say over here we have an ethyl group, so a CH2, CH3. These are 4 different groups, aren't they, right? I have a methyl, that's one group, chlorine is another group, a proton, and an ethyl group. So the trap that students will fall into sometimes, not you guys, of course, but other students might fall into, is they'll say, well, this is a carbon and this is a carbon, therefore it's not a chiral center. That is not true, because we have to have 4 different, what, starts with G, ends with groups. That's right, groups. And therefore, this would be a chiral carbon. So this here, we'll put this, son of a gun, keep wanting to switch colors here. So this is a chiral carbon. All right, and we'll look at some other examples of chiral carbons. It says here, how many stereocenters are present in the following compound? Just as a refresher, if you have a CH3, so if you have a methyl group, or if you have a CH2, okay, these 2 carbons, so this carbon and this carbon here, these are achiral. Okay, those cannot be chiral because the carbon in red on top is attached to 3 hydrogens, and the carbon below is attached to 2 hydrogens. Therefore, it's impossible, for example, for this carbon here, that is not a chiral carbon. But if I look at this carbon here, I'll put a little star by it, this one here, that would be a chiral carbon because I have a proton, I have a methyl group, I have an oxygen over here, and then I have a CH2 over here. Now, I didn't even have to examine the entire groups to be able to figure that out, but that would be a chiral carbon. And so let us highlight that one with the highlighter. So there, that's a chiral carbon. Another chiral carbon in the molecule would be this one right here. This would be a chiral carbon. I have a chlorine, I have a hydrogen, I have an ethyl group, and then I have this entire thing out here. So those are 4 different groups, and therefore that would be a chiral carbon. What else? Are there any other chiral carbons in here? You know, a trap that you might fall into is thinking, well, anything with a dash and a wedge is a chiral carbon. But this is not a chiral carbon because it has 2 methyl groups attached to it, so 2 groups that are identical. So that is an achiral carbon. Other stereocenters, so stereocenters in that molecule, technically you could make a geometric isomer of those 2 carbons. I could have that like in this way, or I could have the bond coming off in this direction. So technically those are stereocenters as well, but I won't ask anything, you know, or I ask you to give me the number of stereocenters having a double bond in it. You should just know the difference between cis and trans, you know, and know that they are stereoisomers of each other. Anyhow, so the total number of stereocenters in this molecule would be 4. Would be 4 stereocenters total. Let's take a look at the next question, which has some interesting compounds on it. And it says, which of the following pairs of stereoisomers are related as enantiomers? And you remember that enantiomers, if you don't remember, I'll help you out. They are non-superimposable Mirror images. Mirror images. And we said, for example, our hands, right? If you hold up your two hands, they are mirror images, but they are not superimposable upon each other. You can't put a right hand in a left glove. So there we go. So that's what we're looking for. And I mean, we could spend a lot of time looking at these, but hopefully you can kind of pick them out here. If I look at A, I could just ask you the question. You could either type in the answer in the chat or unmute your mic. Is there an enantiomer to A here? Is there a compound that is the mirror image of this compound?
B?
No, it's not B, because you see that you see that here that the amino group and the hydroxyl are on the same side, but in A they're on opposite sides. I heard somebody say something else.
C.
I said C.
Yeah, sorry. Okay, so it's C. Yes, A and C, they are enantiomers of each other, right? If you were to cut I'm putting my finger over the one in the middle, acting like you can see that. So if you're to block out B, you can clearly see that A and C are just reflections of each other. I'll ask you the same question about B. Is there a molecule that is a mirror image of B?
D.
Yeah, it's D. Absolutely. Right? D is just the reflection of B. So these are enantiomers as well. All right. And that's all you have to do is to find enantiomers, is just find the mirror image. And these ones are pretty clearly laid out for you, I think. The next question deals with the number of stereocenters in a compound. It says progesterone, which is present in humans as a single diastereomer. It says here it has 6 stereocenters. Human progesterone is one of how many possible stereoisomers? Well, you might remember that I went over this in class one time, and I said the number of stereoisomers, possible stereoisomers, stereoisomers, is equal to 2 to the power of n, where n, I'll put here where n is equal to the number of stereocenters. And so if this compound has 6 stereocenters, what's 2 to the power of 6? 2, let's see, 2 times 2 is 4, times 2 is 8, 8 times 2 is 16, times 2 is 32, times 2 is 64. So it means there would be 64 possible diastereomers. We'll put here 64 possible. We'll put here stereoisomers. This is the way they phrased it, stereoisomers. And don't worry, I'm not going to give you this question and say, you know, it's got 86 stereocenters, but you don't have a calculator. No, it'd just be something you can figure out in your head. The next one deals with, it says dextrorotatory compounds. They rotate plane polarized light in which direction? And you might remember that we looked at, you know, chiral compounds. So let's say we had a chiral compound. I'll just come up with one off the top of my head. Let's say we have this compound and we have its mirror image. So I'll draw the mirror image of that compound the best I can anyway. So these two compounds are enantiomers of each other. And I said enantiomers will have the same, sorry, I'm getting a message from my wife. Anyhow, so enantiomers have the same physical properties, right? They're going to have the same melting points, boiling points, and those kinds of things, densities. And the way that you can differentiate between enantiomers is by the way, the direction that they rotate plane polarized light. So I don't know what the optical rotation is for either of these molecules, but the concept is this. If this molecule rotated plane polarized light, let's say positive 10 degrees, this molecule is going to rotate plane polarized light negative 10 degrees. So they rotate plane polarized light in equal and opposite directions. And when the light is rotated positively or to the right, so we'll call this clockwise or to the right, okay? Or we can say positive, okay? This is dextrorotatory. If the plane polarized light is rotated in a counterclockwise fashion to the left, it gives us a negative rotation in terms of its degrees, number of degrees. We call that levorotatory. Levorotatory. So dextrorotatory rotates plane polarized light to the right. And you can think of dextro. I always think of it in French. I don't know how you say right in Spanish, but in French, right is droite. So it's a word that starts with the letter D. Anyhow, a little bit more about stereochemistry. This is kind of a fun one for anybody who's ever, maybe administered drugs before. It says here the drugs Prilosec and Nexium both contain the same active ingredient. They're proton pump inhibitors. They help with heartburn. But Nexium contains a single enantiomer, so one enantiomer, but Prilosec is a racemic mixture. A racemic mixture is a 50-50 or 1-to-1 or whatever, 50-50 mixture of two enantiomers. Okay, so it says here, which drug will be more effective if you receive a 20 milligram dose of each? So can anybody answer this for me? Which one of them would be more effective if I gave you 20 milligrams of it? Which one would have Sorry, go ahead.
The one that doesn't have the 50-50 mix, because doesn't the other half of it do completely nothing, basically?
That's right. It's not that it's nothing. It just doesn't have the desired therapeutic effect, right, Sean?
Yeah.
Yeah, absolutely. It might have a side effect, or it might have no effect at all. It might just get metabolized and excreted in the urine or the feces, or come out in your breath or your sweat. So you might just metabolize it. But you are correct. So the one that's going to be more effective will be the one that's the single enantiomer. So let's write here. Come on. So we'll put single enantiomer, Nexium, will be more effective. There we go. More effective. All right. That junk up and moving right along. Okay, question 59. How many different triose sugars exist? This is a question I would never ask you in 100 years because I never asked you to memorize any triose sugars. But I'll just show you what they would be, and we can discuss them kind of quickly. We can have this molecule, and this is a molecule that we did look at in detail one night. It's one of the simplest possible carbohydrates. This is D-glyceraldehyde, and then we can have L-glyceraldehyde, which is its enantiomer. So I'll just draw that out here. This is the enantiomer. So this is, and again, you don't have to have this memorized, glyceraldehyde. And then the last one is that you can have dihydroxyacetone, which is this compound here. So this is called dihydroxyacetone. Again, I repeat, you would not have to have these memorized. My question to you would be, if I look at D-glyceraldehyde or L-glyceraldehyde, would these be aldoses or ketoses? Would these be aldoses or ketoses?
Would they be aldoses? Yeah.
Yeah, they're aldoses, right? And I just wanted to make sure that you remember that when you have CHO like this is the same thing as an aldehyde, right? So these are aldoses. Aldoses. Not only that, they are aldotrioses, right? Because they have 3 sugars. Dihydroxyacetone is not an aldose. It's a ketose because it's got a ketone in it. Anyhow, there we go. So let's move on to the next question, which says, how many chiral carbons are present in the straight chain form of glucose? What about the cyclic ring form? You don't have to have the structure of glucose memorized. I'll draw it out here for us. So I'll put here D-glucose. So, oops, I'll have to fix that a little bit here. So this, there we go. So this is D-glucose. So I'll let you think about that, how many chiral centers are in there. So this is the straight chain. Straight chain form. And then I'll draw the cyclic ring form. I will draw it as a Haworth projection or a Haworth projection, depending on your pronunciation. I'm going to leave the proton. Well, maybe I'll draw the protons. Oops, I made a mistake there. So it's supposed to be going up. I drew it as alpha. And there we go. So how many chiral centers are there in the straight chain form? Does anybody know? There are different numbers. Go ahead.
It's 4?
Yeah, it's 4. Elena, is that you?
Yeah.
Hey, all right. Thanks for showing up. Great. Yes. So this is a chiral center. This is. So in the straight chain form, there's 4. Now, I don't expect you to be able to draw this or anything. But what happens is this oxygen that I'm highlighting in blue, this is the one that forms the hemiacetal with this carbon. Right? So this oxygen that I highlighted in blue is actually this oxygen here. Okay, and I'll highlight this oxygen in green, and that's this oxygen over here. And so in the cyclic form, you actually produce an extra stereocenter, and it's the anomeric carbon. This is a stereocenter. So in this molecule, we have 1, 2, 3, 4, and we also have a 5th one over here. So we go from 4 stereocenters to 5 total stereocenters. So kind of interesting how you increase the number of stereocenters when you go from the straight chain form to the cyclic form, cyclic ring form. Okie doke. Let's take a look at a glucose molecule. It says here, if the following is, it should say is the following structure. I'll fix that. Is the following structure alpha or beta D glucose? I know you all know the answer, that this is alpha, right? And this is, we'll put here alpha D glucose. And we'll put here because anomeric, the anomeric OH is pointing down, okay? So down is alpha, and then of course beta is when it's pointing up, and I told you the way to remember that is beta. Kind of looks like a butterfly, and butterflies fly in the sky, whereas alpha kind of looks like a fish, right? Anyhow, and fish are down in the ocean. Okay, let's move on from there. Question 62. The 2 simplest sugars are glyceraldehyde and dihydroxyacetone. We looked at dihydroxyacetone earlier. It's this molecule here. I'll redraw it, but just so you have that bug in your ear. Dihydroxyacetone does not rotate plane polarized light. Why is that? I'm going to redraw the structure, and I want somebody to tell me why this doesn't rotate plane polarized light.
Is it because it's symmetrical?
It's no, it's not because of the symmetry in the molecule. Think about what does an organic molecule or any molecule have to possess in order to be active in terms of plane polarized light, in order to rotate plane polarized light. What's the criterion that have to be met? There's one thing that a molecule needs, at least one. Starts with C, ends with Chiral.
Chiral?
Yeah, there's no chiral carbons, right? Dihydroxyacetone, no chiral carbons, okay? Therefore, will not rotate plane polarized light. Sometimes we call this being optically inactive. So let's go back it up, right? I told you, like, what if, for example, and I don't have these memorized at all, but if, let's say if D-glyceraldehyde, if it rotated plane polarized light, right, positive 10 degrees, then L-glyceraldehyde would be minus 10 degrees. And why? because they both have a stereocenter. Only one, but they have a stereocenter. Whereas dihydroxyacetone has no stereocenters. All right, no stereocenters in the molecule. Why is that? Well, this carbon here only has 3 total groups attached to it, so that can't be a chiral center. And both of these are CH2s. And I told you before that when you have a CH2, that cannot be a chiral center by definition because the carbon has 2 hydrogens attached to it. Let's move on to question 63. A glycosidic bond. We talked about when you make a disaccharide from 2 monosaccharides. For example, if you make maltose, which is when 2 glucose molecules come together. If you make lactose or what else? Cellobiose, things like that. We said that a glycosidic bond occurs when a blank functional group on a sugar reacts with a blank functional group on the other sugar. Well, I'm not going to spend a lot of time on this, but it's when the hydroxyl or the OH of one functional group, right? A hydroxyl reacts with another hydroxyl, and you end up losing water, right? You lose water, lose H2O in the process. Now, we went over this in detail, but if you want to take another gander at that, for example, you could take a look at, again, something like glucose plus glucose, and you could verify that you form maltose plus you lose water in that process. The next one is one that I don't think I would ask you this specifically, the question this way, but we can discuss this as a class, is where do trans fats come from? So you know that cis fats are the kind of unsaturated fats that are found in plants. I'm just going to come up with one out of my head here. This is not any kind of specific trans fat, because normally the double bond occurs at carbon 9, and this is not occurring at carbon 9. But this is a cis fat, and cis fats are naturally occurring. And what happens is, does anybody remember the reaction that happens that causes the formation of a trans fat?
Isn't it when it the molecule gets like basically pumped with a bunch of hydrogens in it, hydrogen ions?
You're right, not hydrogen ions, it's hydrogen gas. So it's when you take H2 gas, right, and a metal catalyst, and you isomerize that double bond. It gets converted from cis to trans. Can anybody tell me the name of that reaction?
Hydrogenation.
Damn right. Sorry, I'm just counting my carbons here to make sure that I'm not making any 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry, my molecule kind of changed colors here. But anyhow, I went from a cis fat to a trans fat. Okay? Yeah, so what happens is we go from, these 2 hydrogens to being cis to being trans to each other. And trans fats are unnatural, and they've been linked to atherosclerosis and, hardening of the arteries or whatever. Anyhow, so these are synthetic. They can occur naturally, but they're very rare in nature, and related to heart disease. We could say heart disease. Anyhow, just kind of a fun thing. And I didn't mean it was a fun thing, but anyhow, and this reaction is called hydrogenation, right? And even if you go up to somebody on the street and you'll say, "Have you ever heard of hydrogenated vegetable oil?" And they will usually say, "Yes, I've at least heard the term." They might not have an idea what the hell it means, but that's what hydrogenation is you take an alkene and you subject it to hydrogen. Now, normally in the alkenes chapter, if we had, let's say, let me make it something simple here. If we had something like, trans 2-butene, and we treated that with, hydrogen in a metal catalyst like palladium, platinum, or nickel, we would end up forming an alkane, right? But that's when the hydrogen actually adds to the molecule. And this reaction here, I would say the mechanism probably isn't all that well understood as to how this happens. But it does happen, and we don't like trans fats in our diets, despite how tasty they might be. I'll let you read the next question while I flip over my sheet here. It says an alpha-1 for a glycosidic bond is found in what types of molecule? What types of molecule in plants? And the answer to that is starch. Starch and amylose. Amylose and amylopectin also does have alpha-1 for glycosidic bonds. That's more of a memorization thing. But remember, you have alpha-1 for glycosidic bonds and alpha-1 or 1,6 branching, alpha-1,6 branching in amylopectin. Sorry, what was I trying to say? Yeah, you have alpha-1 for glycosidic bonds in glycogen as well, but glycogen is the storage molecule of glucose in animals. And this question specifically asks us about plants. So that's why we're going to put amylose as our answer. This one here next one is more of a discussion problem. It just says name 3 roles of lipids. The first thing that always comes to my mind is, I won't tell you. Can anybody come up with any kind of role that lipids play? And don't say something like tasty food or something, like thinking in terms of biochemistry.
I put down energy storage and energy source.
I'd say, yeah, energy, right? We'll just put that down. Both are perfect, yeah.
Protection from like
Yeah.
surrounding stuff.
Yeah, insulation, and I'll put what you're saying, which is shock absorption. Absorption. Yeah, those are perfect. There's another one that I'm thinking of. I'm going to give you a clue. It's very rare that I give my students clues. Right?
So it is the plasma membrane.
Yeah, the phospholipid bilayer, right? Yes, those are phospholipids, right? This is what I'm trying to draw here. Anyhow, yes. So let's just call it, we'll put, I wrote down cell wall structure, Elena. That's fine with me. Other ones that might not come to your mind, I put hormone production as well, right? Anyhow, again, this is the kind of thing that you wouldn't have to come up with these on a multiple choice exam, right? As one of my students so eloquently put it one time, the answer's there, right? The answer's in front of you. You just have to choose it. Anyhow, let's take a look at this one here. This is a good question. What are the components of a triglyceride? What type of functional groups links these components? Could anybody tell me one of the components of a triglyceride? And I'll start drawing a triglyceride while you're thinking about that. My artist rendition here.
Is it esters?
Yeah, so yeah, the functional group that links the components, absolutely. Yeah, so we'll put this part here. We'll put esters, absolutely. But what are the two, so there are two major components, okay, of a triglyceride. Like,
Isn't it?
Go ahead.
Isn't it a glycerol head and then like 3 fatty acid tails?
Yeah, so glycerol, I would say glycerol is going to be one part. So this part comes from glycerol. So glycerol is a 3-carbon molecule, 1, 2, 3, and then I have a hydroxyl, and a hydroxyl. So yes, one of them is glycerol, and the other one would be, you're right, the rest, which is, the fatty acids. I'll just grab this too. Anyhow, and then a fatty acid, I don't know, I hope you can see my yellow ink, but anyhow, it would be, yeah, we'll just put any old tail on it here. Fatty acid. I don't know if did I ask you guys about Bob Ross the other day? Have you ever heard of Bob Ross, the painter?
Yeah. Yes, we've heard of him. I'm fairly confident.
Yeah. Anyhow, I feel like the more I lecture online, the more I'm feeling like Bob Ross. I'm like, just add a happy little tail on the end of our fatty acid there. All right, so glycerol backbone attached to fatty acids. And Elena, yes, you are correct. It is an ester functional group, right? If we color coded that, we could say, the ester is, nope, that's not what I was trying to do. An ester is, right, is this part here, right? And there's 3 of them. Okay. The next question, I wouldn't expect you to have the structure of stearic acid memorized in any way, shape, or form, but I'll write it out for you. So it's got 18 carbons. Let's see if I can do this. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18. There we go. So this is stearic acid, which is found as one of the major components of tallow, which is beef fat. And then if I wrote it the structure of oleic acid, so help me God, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's a cis fat. Anyhow, close enough. So this is oleic acid. Stearic acid is common in plants and animals, while oleic acid is found in plants. How does oleic acid differ from stearic acid? Well, I won't ask you to go on a big tirade about this, but oleic acid is an unsaturated fatty acid, okay, fatty acid, while stearic acid is a saturated fatty acid. And what's the difference between them? Well, if I have two molecules of stearic acid, they're going to pack together much more efficiently. So that explains why stearic acid will have a higher melting point, a higher boiling point. And stearic acid is actually a solid at room temperature. So that explains that. Now, oleic acid, because of that olefin or that cis, or sorry, that cis double bond in there, what it does is it puts like a kink in that hydrocarbon chain, which prevents the efficient stacking or packing of oleic acid molecules, and therefore you're going to have less London forces between those molecules, and less London forces means it's going to be a liquid at room temperature. And the difference is basically saturated fat versus unsaturated fat. Okay, let's move on and describe the structure of phosphatidylcholine. And you don't have to be able to regurgitate the structure of phosphatidylcholine. I can do that for us, so I'll help you out. So it's got a glycerol backbone. So we have the glycerol backbone. We do have two fatty acids. So we'll just put, a generic fatty acid on this one, and then another one over here. Now, a choline is this molecule here. It's when you have a hydroxyl, 2 carbons, right? And then you have a nitrogen with a positive charge like this. So the phosphatidylcholine, and again, you don't have to have this memorized. I'm just doing this for us for the sake of discussion. We have, there we go, 1, 2, and then we have, right, the charges balance out like this. What class of lipid is this? Who could tell me what class of lipid this is? And that's not a loaded question.
It's a phospholipid, right?
Oh, damn, exactly. This is a phospholipid. Exactly. And what role does it serve in the body? Well, let's just circle that in blue. What role does it serve in the body? And it's going to be involved in cell membranes, right? It's going to, we'll just put found in cell membranes. Nothing fancier than that. We'll just leave it at that. Phospholipid bilayer. So it's an example of a phospholipid. You get the two fatty acid tails and you have the polar head group, right? So this is what's being represented, right? So the circle here, that's this part. This is the polar head group, and the rest of it is the two fatty acid tails. And I'm sure that if anybody in this class has taken biology, you've drawn this before. And I hope this is one of the things you took home from the lipids chapter, is what a phospholipid is actually made of. The next question, question 70, says, draw the straight chain form of D-allose, the C3 epimer of glucose. Again, I would never ask you to just draw mannose. No, that's not a question. I want you to understand what the hell is going on, not memorize the structure of every sugar from here to kingdom come. So I'll help you out by giving you the structure of D-allose. If you take advanced organic chemistry, yes, in that class you do have to memorize the structure of a couple of sugars, but not in Chemistry 102. That is not part of our SLOs or our student learning outcomes. But if I give you D-allose, we spent quite a bit of time learning how to draw the ring form, right? And I told you to first, you kind of knock the sugar over, right, Timber, right? And this is really the artist's rendition here. It's not my neatest work, but you draw something like this. And then I went through all the steps that are involved in drawing the 6-membered ring. I'm not going to reteach that tonight, but a shortcut that we came up with in class is that any groups that are on the right-hand side here, these groups are all going to be pointing down. So when I draw my 6-membered ring, we'll start by drawing this 6-membered ring with the oxygen in the top right corner. This part, the CH2OH, that never changes. It tells us in the molecule that they want us to draw the alpha, and that is designating the anomeric carbon hydroxyl as being pointing down. And then the other hydroxyls on 2, 3, and 4, right? This is carbon 2, 3, and 4. Those are all going to be pointing down as well. And there you have it, folks. This is going to be the ring form of D-allose. So this is alpha D-allose. There we go. All right, so everybody should be able to do that. We spent quite a bit of time practicing those. Okay. Anyhow, let's move on to something else. Moving right along. What feature makes a given carbohydrate reducing or non-reducing? List an example of both types. Well, a reducing sugar, right? Reducing sugar has free OH, it has a free hydroxyl at the anomeric carbon, right? And there are many examples that you could give me for this. You could say glucose, fructose, okay, etc. You could say galactose, lactose, right? But non-reducing sugars, reducing sugars do not have a free hydroxyl. They'll have an alkyl group attached to that hydroxyl. So it'll be an alkoxy. Non-reducing sugars, I just want you to tell me, could anybody name the one non-reducing sugar that I asked you to memorize? Again, not a trick question.
It was the table sugar, correct?
Hot diggity darn. And table sugar has a name.
That it does.
It's sucrose, Sean.
Okay. That's what I thought. I didn't want to
Yeah.
say the wrong sugar and feel dumb.
Sucrose, table sugar. Sometimes they call it dextrose on food labels, dextrose. Beet sugar, right? We'll even put a big yellow thing here. All mean the same thing. Don't you just love how chemists love to come up with, 3 or 4 different ways to describe the exact same thing? All right, glycogen. Oh, we discussed this earlier. Glycogen is very similar to what other material? Who can tell me? Glycogen is the main storage form of glucose in animals, including humans. Anyone?
It's similar to amylose and
It's not.
amylopectin.
It's amylopectin, right? Because amylose is just glucose units linked by alpha 1,4 linkages, right? It's just a straight chain, whereas amylopectin has the branching, right? So and glycogen definitely has branching. So amylopectin. Okay, so we'll put here glycogen has. And this is a question I think I might have asked you on an exam. I can't remember if it was this semester or another semester. But glycogen has more branching. We'll put here shorter branches. It also has a different solubility, but that's not covered in our book, so we'll skip that. And amylopectin. Why do I keep doing that? We'll also put here, let's put animals on top here. We'll put amylopectin. It's found in plants. And then, of course, less branching, and the branches are longer. All right, and we looked at some nice pictures of those. Why are lipids insoluble in water? I'm sure that everybody who's online right now could go up to a student in Chemistry 101 and explain this to somebody. But let's kind of put it succinctly here. And the way that I would do it is I would say they contain, carbon, hydrogen, So carbon-carbon and carbon-hydrogen bonds, okay, which are simply just nonpolar, and therefore insoluble in H2O. Now, if you think about all the different lipids that we looked at, right? Lipids is the only chapter that, or one of the first chapter where it wasn't focused on a specific functional group or 2 or 3 functional groups, right? Lipids, we saw all kinds of different functional groups in lipids, right? We saw phosphate esters, amines, esters, carboxylic acids, alcohols, ketones. What made them what they are is they're insoluble in water. And the reason why lipids are insoluble in water is because of so many carbon-carbon and carbon-hydrogen bonds. If you don't believe me, go back and look at the structure of all of the different lipids that we've looked at. The next one, it says here, what is the polyalcohol component of all triglycerides? This wasn't meant to be a tricky question or anything. It just means the polyalcohol. I just thought I'm not a huge fan of this question, polyalcohol. Does anybody know what it means? What I'm getting at? Maybe I think the question's tougher than it is. What polyalcohol is found in all triglycerides? We looked at it tonight.
Is it glycerol?
Hot damn. Yep. Just glycerol. I didn't mean anything fancier than that. But, you know, it's a polyalcohol, right? Because it's got more than one alcohol in it. So thanks, Will. The answer is glycerol. Okay. And it says here, could you give the IUPAC name? So if I redraw it here in blue, so underline common in black, and then IUPAC, I'll do it in blue. So if I redraw the molecule in blue, could anybody come up with an IUPAC name for it? Maybe not, because when we have a hydroxyl as a functional group, we call it a hydroxy. So the way that you would name it is you would say, okay, the longest carbon chain has 3 carbons. So it's got kind of a funny name. You would call it 1, 2, 3 trihydroxy propane. Now you can see why people like to say glycerol. So it rolls off the tongue much easier than 1, 2, 3 trihydroxy propane. All right, let's take a look at what's the minimum number of carbons in an amino acid. If we just draw a generic amino acid, so if we put our amine here, and then we have our carbonyl over here, our carboxyl group, and we have an R group. Well, R can be H, right? If you have glycine, R is H. So the simplest possible amino acid you could have would be this, okay? And how many carbon atoms are in this? There's only 2, right? So that's the minimum number of carbons you could have in an alpha amino acid would be 2, all right? Because this is glycine. And again, you don't even have to know the name of glycine or anything. You just have to know that that's the least amount of carbons you could have. This next question says, from the list of amino acids, identify the following structures. Look, I would never ask this, okay? This is something that even in advanced organic chemistry, I don't force my students to memorize all the amino acids. That is something that if you take full year biochemistry at the 3000 level in university, then you will be asked to memorize all the amino acids in like the first week of class or something, but I would never expect you to do that. But let's see if we can figure them out. The first thing that I notice is only one of them has the word phenyl in it, and it's the one with the phenyl. So this must be phenylalanine. Another thing is that if you remove the phenyl, if you were to subtract this part here, you would have a CH3 over here. So if I just have a CH3 on the end, that must be alanine, which is this one here. The other two, the only way to differentiate those is by memorization. But we did talk about cysteine and forming cysteine bonds, right? And that was using a sulfide. So this one here, this is cysteine, and then this one here is serine. And we talked about serine proteases. Again, you don't have to have the amino acids memorized. That's why I kind of blew over that question kind of quickly. Hey, could anybody explain to me in their own words, and it doesn't have to be beautiful, what a Zwitterion is? A Zwitterion? Again, doesn't have to be fancy.
Is it a molecule that has a neutral charge?
Has a neutral charge, but what else does it have? Because if I
Separated
have,
by positive and negative charge groups, which
yes,
makes it
right?
neutral.
Because, exactly, because if I have benzene, that's a neutral molecule, but it has no charge, right? So a Zwitterion would be a molecule that has both a positive and a negative charge, okay, which balance out to give you a neutral molecule. If we draw the Zwitterion of glycine, which we could do pretty quickly, which is how it would exist at physiological pH anyhow, I would have a negative charge on this oxygen here, on this carboxylate, and I would have a positive charge on my nitrogen. So that is a Zwitterion. All right. Question 76. We have an amino acid here. This is lysine. Anyhow, again, I don't expect you to have that memorized, but this amino acid is lysine. And it says, what would it look like if you were to put it in a pH below 1? That is seriously acidic, my friend. That's really highly, very highly acidic. So we'll put here strongly acidic. We'll put acidic with double exclamation point. Sorry, did somebody, Sean, were you going to say something?
I would say it'd be denatured, but I'm not sure what it would look like.
So it would not, yeah, so denaturation would not occur. So denaturation deals only with peptides. So denaturation is a concept that is only involved with peptides. When you have secondary and tertiary and quaternary structure, then a peptide can undergo denaturation. This is just a single amino acid. So one stinking amino acid. If I took this and I put it in HCl, right, which would maybe have a pH of equal to 1, right, something really acidic, what's going to happen? This carboxyl group, this is already a carboxylic acid. That is not going to be protonated further. But remember that amines are NH2, right? Amines are organic bases. And what's the definition of a base? A base is an H plus acceptor, right? And what does HCl liberate in solution? It liberates H plus and Cl minus. So that means that these two amino groups, right, these can both take on an extra proton in a strongly acidic environment. So instead of being just NH2, they're going to protonate to be NH3 positive. So fix this up like this, NH3 plus. I hope you remember that we went over this one night in class. We practiced what would happen if you put an amino acid in a strongly basic environment, in a strongly acidic environment. So anything that can be protonated, which would be a base, will be protonated. Okay? I hope that helps. If you need to look over that, make sure to take a gander at that. Again, you want it to draw anything, but make sure you at least understand the concept. Again, this question here, number 77, this is more of an FYI thing because I would not expect you to memorize how many amino acids have acidic side chains. I would expect you to be able to recognize them, right? They're the ones with carboxyl groups, and there are two of them. There are aspartic acid, and glutamic acid. And there are groups, both have carboxyl groups on them. So you should be able to recognize a basic amino acid, an acidic amino acid, a polar amino acid, and a neutral amino acid. And if you're unsure about that, make sure you look at our notes. So we'll put acidic, basic, polar, and what was the other one? Non-polar would be another one, non-polar. Okay, you have to be able to recognize all of those. All right. Anyhow, draw the hydrolysis of this would be called alanyl phenylalanine. You don't have to name it, but anyhow, I'll help you by drawing out the dipeptide first. So the dipeptide would look something, oops, let's use a better color than that. Let's use black. So I'll start by drawing my, no, I'm just full of mistakes here, aren't I? There we go. Let's start by drawing our alanine. So we have our CH, there we go. There's our methyl group. And there's our carbonyl. And here's our amide bond to the next amino acid. You remember NCC, right? That's where we always start when we're writing out an amino acid. So we'll put our aromatic ring down here for our phenylalanine, and then we'll draw our carboxyl group. So just remember that when we draw dipeptide or a tripeptide or whatever, that we always go NCC, right? NCC. So this would be for a dipeptide. Okay. So remember that we do that. So we have N, right? CC, and then we have NCC. So our sequence of atoms looks good, but what's going to be hydrolyzed is the peptide bond, and the peptide bond is encased in this amide, right? This is the peptide bond. And what's hydrolysis? It's the hydrolysis, right? Breaking it apart with water. So of course I'll use the color blue because water is blue, right? So when I break that apart, then I'm going to cut that, and I'm going to have my N-terminus. I'll have a CH, my methyl group, but now I'll have a carboxylate, okay? Plus, I'm going to have my protonated N-terminus, CH, and I'll put I'm just going to write pH for phenyl, and my carboxylate like that. Okay, so what did I do overall is, right, if I kind of spruce this up here, my H2O, right, my oxygen is there, and then I have two of the hydrogens attached here, and then the other hydrogen was the one that you had from the get-go, was this one here. And that's the hydrolysis of a dipeptide to give you two individual amino acids. So we're breaking what? Primary structure. Right, so we could even write that down. Cleaving primary structure. All right, because the peptide bond is primary, right? Primary structure. Okay, how many atoms form the backbone of a repeating unit of a polypeptide? A polypeptide is another way of saying a protein, but we don't call a dipeptide or a tripeptide. We don't call those proteins. We just call them, small peptides. It's not until you get past 11 amino acids or something that we start calling it a protein. And hopefully you remember that the backbone is this. It's nitrogen, carbon, carbon. Right? That is the backbone. So there are 3 atoms total. NCC. What are the 2 most common forms of protein secondary structure? I'll let you guys answer this one. Who could tell me what that would be? The 2 most common. Even if you can only come up with 1, that's totally fine. Oh, I just got a message from Will. I don't know if you guys saw that. Yeah, does anybody have an idea what the 2 most common forms of protein secondary structure are?
Isn't
The
it a
alpha
beta?
helixes?
You're both right. I heard both of you, and you're both absolutely right. So primary structure is peptide bonds, right? And then we have secondary, which you told me is alpha helices, which is the plural of helix, beta pleated sheets. And then tertiary structure, what is that? H bonding, right? What else? Dipole forces, dipole, salt bridges, Jizz, shoot. London forces, right? And we can even have disulfide bonds. Just draw it like that. And then quaternary structure is basically the same thing as tertiary structure. Okay, so when you name a polypeptide chain, and we didn't look at a whole hell of a lot of nomenclature of polypeptides, dipeptides, tripeptides, so on and so forth. It goes over in the book a little bit, but you should remember that you start at the N terminal or terminus, and you go to the C terminal. And again, Mr. Deon likes to say terminus instead of terminal. Either way is perfectly fine, but right, we always follow the order, right? We go from N to C. So NCC, so we start with N terminus, right? So our N term, and then we go to our C term. Okay. Number 82 says the identity of the R groups contributes most significantly to the what structure of proteins? Well, we said that the primary is based off of peptide bonds, so that has nothing to do with R groups. Alpha helices and beta pleated sheets, those are due to hydrogen bonding from the amide bonds, but tertiary structure and quaternary structure is going to be a result of the effect that the R groups have on one another. So I would accept, I'm looking at my answers, and I wrote tertiary. If you wrote quaternary, that would be okay with me too. So either one is fine. We'll put tertiary or quaternary. There we go. Number 83 is just kind of an FYI, just kind of a food for thought thing. It says, explain why soap would effectively denature many proteins. Well, you think about a soap, which has a hydrophobic portion and a hydrophilic portion. And proteins have hydrophobic portions and hydrophilic portions as well, right? In a protein, we think of the tertiary structure being such that the nonpolar R groups are going to be inside the protein, and the polar R groups will be on the outside of that protein. And therefore, soap is going to be attracted to those forces, right? So the nonpolar part of soap is going to be attracted to the nonpolar part of the protein. What's that going to do? It's going to disrupt the tertiary structure. And that's all that's happening when soap encounters a protein. It's just disrupting the tertiary or quaternary structure, which causes denaturation, of course. So let's try to summarize this. I wrote it down already. We'll put here, soap has a hydrophobic and hydrophilic side. Proteins have hydrophobic and hydrophilic sides. The soap is attracted to these, and I'll just make it simple, and forces the protein apart. You could probably come up with a longer, explanation, which might have a little bit better detail in it, but this will suffice for now. Number 84, a little, kind of fun drawing here. It says draw 2-amino propanoic acid. Well, I think everybody can draw propanoic acid. That's a 3-carbon carboxylic acid. Like this, if I have 2-amino, then I'd have an amino group here. The next one is kind of tougher. It says 2-amino 3, and then you've got this 4-hydroxy phenyl in bracket propanoic acid. Let me show you how you would analyze that. You'd start with the parent propanoic acid, so we'll start there. And then it says we've got a 2-amino, so we'll put the 2-amino. Then it says at carbon 3, so this is 1, 2, 3, we have a 4-hydroxy phenyl. So look, if we have a phenyl, which is this, okay, if we have a 4-hydroxy, that means 1, 2, 3, 4. We've got a hydroxy out here. So that means this molecule would look something like this. And then it just says, do they look familiar? Let's make it simple. They are both amino acids. amino acids. Okay, and again, I wouldn't expect you to be able to memorize all of the amino acids, but this one here, this is alanine, and this one here is tyrosine. Again, you don't have to have those memorized. Also, this one here, this is more of a just kind of a discussion problem, because there's going to be no problems on the final exam where you have to just, come up with a bunch of different answers. It just says, what are 3 roles of proteins in the body? I would, just kind of keep this one simple. I'd put something like antibodies, right, are a type of protein, right? Enzymes are also a type of protein. Enzymes, hormones also can be proteins, like insulin. Okay, so things like that. Anyhow, let's just keep that one simple and move on to something else. Number 86. Oh, I love these kind of questions. What's wrong with the following statement? Enzymes shift the chemical equilibrium to more heavily favor products. Okay, well, the answer to this is enzyme. This would be if you shifted the equilibrium to more heavily favor products, that's affecting the thermodynamics of it. But enzymes do not affect the concentrations of products. They affect what? The rate of reaction, right? Enzymes just increase the rate of reaction. So we'll put here, enzymes serve to lower what? Activation energy. And I know this is something you all learned in Chemistry 101 of a reaction in order to increase the reaction rate. Okay, doesn't affect the equilibrium of the concentrations of it doesn't affect the concentrations of products and reactants at equilibrium. It only makes the reaction go faster. That's all an enzyme does. It has to do with kinetics, right? Kinetics. Okay, there we go. Number 87 says, in competitive inhibition, does the inhibitor bind to the active site or to an allosteric site? Is this an example of a reversible or irreversible inhibition? Now, if we have some kind of substrate here, there we go, there's our substrate, and this is our binding site here, this is our active site. Well, we can have the inhibitor, right? But it says in competitive inhibition, we could also have another inhibitor, which might not be the exact same, but will also be able to fit into the active site. So the battle becomes, a competition between those two. So it binds to, in competitive inhibition, it's going to bind to the active site. And this is an example of reversible inhibition, right? If you have irreversible inhibition, that would be something like we said, a poison, okay? So let's write here, it binds to the active site, and this is reversible. An example, the classic example would be a drug, right? Because you take a drug, the drug's going to bind to the active site and cause a desired therapeutic effect. But what happens to the drug over time? Some of it will dissociate from the active site and get metabolized. And that's why if you take a dose of ibuprofen, it's not good for the rest of your life, because you metabolize that. Why? It's because, again, it doesn't stick to the active site. It is reversible, right? That's a reversible process. So some of it will remain bound, and then some of it will dissociate, get metabolized, and eventually the concentration will drop so low that you will not have the therapeutic effect of that drug. What molecule is primarily responsible for conserving the energy released in catabolism? Nothing fancy here. Can anybody tell me what molecule it is while I take a drink of water? It stores our energy in the form of
Glycogen?
No. How do we conserve most of the energy that we get from catabolism? What did we add up? What molecule were we always adding up at the end? We were counting up what molecule?
ATP.
Yeah, ATP. ATP. There we go. Shouldn't write with a highlighter, but what ifs. What is the most readily used energy source in the diet? I'm not sure if I mentioned this in class or not, but the answer is a carbohydrate. You can get more energy from a lipid, but the fastest source of energy is going to be a carbohydrate like glucose. Okay, and that's why people who are running, marathons or something, or if they don't hand them, they don't hand them bacon while they're running, right? Because you can get more energy from fat, but they hand them like, I don't know, sugary juice or a chocolate bar or something because it's metabolized so much faster. What are the end products of glycolysis? Well, I mean, this is just a matter of memorizing that you end up with pyruvate from glycolysis, ATP, and NADH. Anyhow, let's move on from there. The next one, oh, this is a good question. I like this one. I dig it. It says, what is a kinase? When an enzyme has the term kinase, what type of reaction do you expect it to catalyze? Who could tell me? What kind of group? This was in my videos that you all watched with bated breath.
Is it a phosphorus?
It's a phosphate. Yeah, close enough. Close enough. It's a phosphate group. Yes. So kinases transfer phosphate groups. The reason why kinases are so dang important in chemistry and biochemistry is because kinases are targets for a lot of different, diseases like cancer and things like that. So most people who work in the drug industry who are biochemists will be experts in all the different kinases that are out there. Anyhow, define gluconeogenesis. Gluconeogenesis is just the genesis or the making or the synthesis of glucose from non-carbohydrate starting materials. Okay, so we could write that down. So, and this would be just kind of a matter of looking over it. Gluconeogenesis, okay, is a metabolic pathway that results in the synthesis of glucose from non-carbohydrate starting materials. That's it. Hey, what does hypoglycemia mean? Can anybody tell me?
Low blood sugar.
Yeah, it's low blood sugar. Low blood sugar. I don't have your old ACS final memorized, but I do remember that question. That was actually one of the questions on it. It said if you have low blood sugar, and it said hyperglycemia, hypoglycemia, and then two other answers that I don't remember. So sorry, I don't have the new exam memorized or anything. But anyhow, hey, does anybody have a friend who's diabetic? I used to hang out with a guy when I was working in Boulder who was diabetic, and we'd go to Five Guys Burger, and Fries, and he would, crank up his insulin pump. And why did he do that? Can anybody tell me why he did that?
Because it lowers your glucose levels.
Yeah, by converting it into what? And converting it, well, here, converting it to, anybody know what it gets converted into? Stored in your liver as? Starts with the letter G. Ends with glycogen. Yeah, it stores it as glycogen. Thanks. Okay, number 95. Did I not do a break? Oops. Anyhow, we'll wrap it up here in a few minutes. Yeah, we're getting close to the end. What molecule serves as a signal to increase the rate of reactions in the citric acid cycle? Well, I'd say there's a couple of different molecules. I would accept either ADP or AMP. Right? All you have to know is that if you have an excess of adenosine di or adenosine monophosphate, that's a signal that you're gonna require an increase of the rate of those reactions in the citric acid cycle, right, to produce more ATP. The next one is kind of in the same vein. It says, what molecules serve as signals to decrease the rate of reactions? Well, that's going to be kind of the opposite. ATP will be one of those, right? NADH would be another. And FADH2. Hey, who knows the answer to number 97? What's the terminal electron acceptor in the citric acid cycle, in the electron transport chain? Does anybody know? Who gets the last electrons?
And then oxygen.
Yeah, it's oxygen. Absolutely. So we'll put here oxygen. Okay, because we take 2 protons plus half an oxygen and plus 2 electrons, and we end up forming water. So yes, Sean, you are correct. It is oxygen. Perfect. How many cycles of beta oxidation can myristic acid undergo? How many FADH2 molecules will be produced? How many NADHs will be produced? Well, first let me start by drawing myristic acid, and it has a total of 14 carbons. So we'll say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, again, it might be a trap to fall into and say, well, it's got 14 carbons, so we'll put here 14 carbons. So 14 divided by 2, because I'm making acetyl coenzyme A, which has a 2 carbon acetyl group. So you might just divide that by 2. Is it 7? And the answer is no. 1, 2, 3, 4, 5, 6. It can actually undergo beta oxidation 6 times. So we'll put 6 beta oxidation cycles. Okay, so 6 of those cycles, but then I end up forming how many acetyl coenzyme A's, right? I end up forming 7 acetyl CoA, right? And I can put all of those through the citric acid cycle. So I'll form 7 times my FADH2s, and each of those are worth 2 ATP, so I'd get 14 ATP from that, and I would get 7 NADHs like that, and I would get 21 ATP, because those are each worth NADH, is worth 3 ATPs. What enzymes hydrolyze sucrose, or what enzyme hydrolyzes sucrose? Does anybody know the name of the enzyme that hydrolyzes sucrose? Remember that most enzymes end in a 3-letter suffix. Does anybody know what that suffix is?
Haze or A's?
Yeah, absolutely. A's. So if it's sucrose, it must be hydrolyzed by sucrase. Right? If it was maltose, for example, it's maltase. If it's lactose, right, it's lactase. Anyhow, so the answer is sucrase. So maltose, I guess we already answered that. So it's maltase. Okay. And then we're going to wrap it up here. Name the 3 types of molecules. Name 3 types of molecules that could be classified as lipids. Who can give me a favorite? A real crowd favorite. Go ahead.
Steroids.
Yeah, that's a great one. So, steroids.
Hormone.
Yeah, a hormone could be. We could have one. A steroid would be a hormone That is a lipid, though.
Is cholesterol?
Yeah, cholesterol is a steroid as well. So these are all steroids. Are there any other ones?
Vitamins?
What's that? A vitamin?
Yeah.
It could, yeah, a vitamin could be like the lipid soluble vitamins. Yes. So you could put I guess lipid soluble vitamins, they're not really categorized as lipids. They're just lipid soluble, I would say. What about the coating on a leaf or on a feather? Does anybody know what kind of lipid that would be?
Wax?
Yeah, a wax. So put waxes would be another good one. What about a triglyceride? Right? A triglyceride or a phospholipid, would be another one. Other ones that I didn't go over in gross and dirty detail in my videos would be things like thromboxanes, which I don't even know if I went over in the slides, but in leukotrienes, in fact, wait a second, hold on, let me look at did we go over those? Yeah, I would have done those in the video. So leukotrienes. Another one would be prostaglandin. The PGs. We call those the PGs, the prostaglandins. What else? A sphingolipid, which is a type of phospholipid, sphingolipid. Anyhow, all of these count. Whatever. Let's move on. Question 102 says, why is an ester like methyl acetate? So let's draw a methyl acetate. So if I have the acetate and methyl, so this is methyl acetate, and you should know how to draw small esters. Why is an ester like methyl acetate water soluble, whereas an ester like myrcil cerotate found in beeswax not water soluble? So I'll draw the structure. I'm going to have to do the condensed version here because it's just way too dang big. So CH2, look at these, 29 of these, okay? So it's a 30 carbon alcohol, sorry. And then over here, this fatty acid has 26 carbons in it. So this is myrcil cerotate, right? There we go. Anyhow, who could give me an answer for this one? And it doesn't have to be a loaded answer.
It has shorter chains. Or the methyl acetate has a shorter chain.
Yeah, shorter chains. I would definitely put that in there. So we'll put here shorter. Why don't we write it like this? Shorter chains allow for efficient. What kind of intermolecular force am I thinking when I put methyl acetate in water? Efficient, what kind of interaction is going to help that solubilize? Well, so what I wrote here about the wax is that those large hydrophobic chains, which are nonpolar, are going to be insoluble in water. But I mean, methyl acetate has two methyl groups, which are nonpolar. But the difference is, like Gabby said, they're very small, they're short, and they allow for efficient hydrogen bonding, right, with the water, right? If I drew a water molecule, for example, okay, I can get efficient hydrogen bonding, whereas in myrcil cerotate, the chains are just so big and floppy that they're going to obstruct any potential hydrogen bonding. Okay, let's take a look at this. What kind of linkage connects these molecules together? Who could help me out with this? And don't say glycosidic. I need specific. Go ahead, sorry. So would this be an alpha or a beta linkage?
Alpha.
Absolutely. So it's alpha to start with. And then in terms of numbering, how would I number this?
Is it 1,4?
Alpha 1,4, absolutely. Alpha 1,4, right? Because this is carbon 1, 2, 3, 4, 5, right? And this is carbon 1, 2, 3, 4, right? And this is carbon 1, 2, 3, 4. So it's alpha 1,4 is the linkage, right? Alpha 1,4 seen here, alpha 1,4 seen there. Okay, and that wraps up the review. Okay, so I'm going to stop broadcasting here just for a second. There we go. And I'm going to stop